Welcome to The Explainer. Today we're diving into complex numbers, but with a really cool twist. We're about to uncover a way more elegant and, honestly, powerful way to think about them. It's an approach that takes these messy calculations and turns them into something super simple and intuitive.
So, let's kick things off with a question. A bit of a puzzle, really. Why is it that multiplying some numbers feels like a total chore, when it could feel as simple as, say, scaling a distance and just spinning a wheel? Turns out, all it takes is a simple change in perspective for everything to just click.
All right, so first up, let's take a look at the standard way of doing things. I mean, it works, but you're about to see exactly why mathematicians were convinced there had to be a better way.
Okay, so typically we write a complex number in what's called rectangular form. Z equals a plus bi. Super straightforward. A is the real part, and b is the imaginary part. And what this does is it gives us a set of coordinates to plot the number on the complex plane. Think of it just like a regular graph, but instead of x and y axes, we have a horizontal real axis and a vertical imaginary axis. So if you want to plot a number like, say, 2 minus 3i, it's easy. You just go 2 units over on the real axis and then 3 units down on the imaginary axis. It's literally just like plotting an x, y point on a normal graph. Simple enough, right? But here's where things get a little messy. This is where the wheels kind of fall off. When you want to multiply two of these numbers together, say a plus bi and c plus di, you're stuck with this formula. And yeah, it's a bit of a beast, isn't it? You've got ac minus bd for the new real part and ad plus bc for the new imaginary part. It's just not intuitive at all. Right? I mean, don't get me wrong, this formula works. It'll get you the right answer every single time, but it doesn't give you any feel for what's actually happening geometrically. There's no story to it, it's just brute force calculation. So you can imagine mathematicians looking at this and thinking, there has to be a better way, right?
Okay, and that brings us to the new perspective, the polar way. Let's completely rethink how we describe our point on that plane, because trust me, this is where the magic really starts.
So instead of the old way, how far over and how far up, we're going to ask two totally different questions. First, how far is our point from the center? And second, what direction do we go to get there? This little shift from coordinates to directions, well, that's the whole key. And that distance from the center, it's got a special name, the modulus. We usually use the letter r for it. And finding it is super easy. It's just the good old Pythagorean theorem. R is just the square root of a squared plus b squared.
Now, what about the direction? Well, that's the argument, and we use the Greek letter theta for it. It's simply the angle that the line to our point makes with the positive real axis. And hey, just a quick heads up here. When you're calculating this with arctan on your calculator, you gotta be careful. Always double check which quadrant your point is in to make sure you get the right angle, because calculators can sometimes get it wrong.
So when you put that distance r and that angle theta together, you get this really elegant expression. This is the polar form. Now, I know it looks a little different from a plus bi, but here's the thing. It describes the exact same point. It's just using distance and direction instead of left, right, up, down coordinates.
Okay, so you might be thinking, why did we go through all that trouble? Well, this is it. This is the big payoff. Let's try multiplying those complex numbers again, but this time we're going to use our shiny new polar form.
Just look at that. Seriously, that horrible, clumsy formula from before, it gets replaced by two incredibly simple rules. That's it. To multiply two complex numbers in polar form, you just multiply their distances, their moduli, and you add their angles, their arguments. That is literally it.
And this is so much more than just a neat little math trick. As a user on Reddit, Infanticide Aquifer, put it so well, this method shows you the true geometry of what's going on. All complex multiplication really is a combination of scaling and rotation. You're just stretching or shrinking the distance from the center, and then you're spinning the point around. How cool is that?
But wait, there's more. This insight doesn't stop at just simplifying multiplication. Oh no. It basically unlocks a bunch of mathematical superpowers, making other really tough operations seem almost trivial. Let's see what else we can do with this.
So, a French mathematician named Abraham de Moivre saw this and realized, hey, we can take this idea even further, and he came up with what we now call de Moivre's theorem. It gives us a super simple rule for finding any power of a complex number. Want to find z to the power of n? Easy. You just raise the distance r to the nth power,
and you multiply the angle theta by n.
Okay, let's actually see this in action. Trying to calculate 1 plus I to the 5th power the old way? That would be a nightmare of expanding brackets. But with de Moivre's theorem, it's this clean, beautiful process. You just convert it to polar form, apply that simple rule to the distance and the angle, and then convert it back if you need to. It's just so much more efficient.
And get this, the same logic applies to finding roots too. And here's where things get really wild. It turns out a complex number has n different nth roots. So think about the number 8. You're probably thinking the cube root is 2, right? Well, in the complex world, it actually has 3 distinct cube roots, and they all lie perfectly spaced out on a circle. Isn't that amazing?
All right, so why does any of this actually matter? Is this just a cool but useless math exercise? Not at all. It turns out this way of thinking has some really profound connections to the real world.
Think about it. Since complex multiplication is, at its heart, just rotation and scaling, it becomes the perfect language for describing anything that spins, oscillates, or moves in waves. And that's why it's absolutely indispensable in fields like electrical engineering, for analyzing circuits, in signal processing, and all over physics.
So in the end, this whole journey from the clunky rectangular form to the elegant polar form is really a powerful lesson in problem solving. It just goes to show you that sometimes the hardest problems don't need a more complicated formula. What they need is a completely different point of view. And that really makes you wonder, doesn't it? What other huge problems could we solve just by looking at them differently?